Okay, so I'm Michael Forbes. I want to tell you about, we're talking about this sort of ideal proof systems and algebraic proof systems the entire day. I want to tell you about some lower bounds for algebraic proof systems. This is joint work with Amir, Ido, and Avi. So there are a lot of results. I'm going to only tell you about a couple of them. I'm going to try to simplify everything as much as possible. So I'm going to tell you some of the results. Then I'm going to try to tell you about two kind of key ideas. Something called the functional lower bound and something called the lower bound for multiples, and I'll define what those are. And then I'll give you some amount of details. Okay, so what's the main sort of proof system I want to talk about is this ideal proof system. Okay, so you have f1 up to fm, and these are going to be polynomials. And you also have x1 squared minus x1 up to xn squared minus xn, and these are going to lie right in your polynomial ring f of x. Okay, and so for notational purposes, so you're going to have n variables, and these are going to be some polynomials of some degree. And for notational purposes, I'm going to say this is the vector f, and I'm going to say this is the vector x squared minus x in an abusive notation. Okay, and so we want to say, suppose that this, really thinking, is this system of equations satisfiable over the Boolean cube? Right, that's why we're adding these axioms here. And so you want to know, is the system unsatisfiable, and if so, how can we prove it? Right, and we sort of already saw this. We're going to say this is this system has a size s IPS refutation. If what? Well, there's sort of two definitions that have been going on today. I'm going to tell you one of them, and I'm going to wave my hands about the other. Okay, so what is the definition here? Is that if there exists two other vectors of polynomials, these are also in your polynomial ring, such that what? They obey the Nullstellensatz certificate condition. Okay, so you have summation gj fj plus summation hi times xi squared minus xi. This is going to equal 1. Okay, so this is a Nullstellensatz certificate saying that this system is unsatisfiable, and Hilbert's Nullstellensatz says that if these are unsatisfiable, then there is such a thing, and we saw statements of this form this morning, right? And the key points here is that, we're proving this basically over the hypercube, so we don't need to worry about things like algebraic closure. And the main point is that sort of, I guess as Pavel basically said, is that because we have these Boolean axioms, in general, it could be that the g and h's have exponential degree. But because we have the Boolean axioms here, we can always assume that these things have at most exponential, so let's say these are degree d or something, exponential in d and n complexity. Okay, so I guess I missed s. So first of all, so g and h are tuples of polynomials, and they're all size s circuits. Okay, so if these are unsatisfiable, I give you a bunch of circuits, and you just want to verify that this equation is true. As Pavel was saying, you can verify this equation is true just by using polynomial identity testing. Right, so this is a refutation showing that these are unsatisfiable. Okay, and so what's the main question here of Grochow and Patesi is, can we develop? We want to find systems of equations f that satisfy some lower bounds properties. So what do we want? Well, ideally, we want the f's to be explicit, right? Ideally, you could write them down. Proving that they exist, as Tony mentioned, the counting arguments don't seem to work here because we want the f's to be succinct. Okay, so this is, I'll write it here. What does that mean? We want ideally the f's to have small circuits themselves. Because in proof complexity, we want to prove, say, that NP is different from coNP. Right? So we want, say, systems of 3 CNFs that require large proofs. So we want the input, which is f, to be small, and we want the proof necessarily to be large. That's why I'm saying what f is explicit means that f should have small circuits. And ideally, we would have that f encodes a CNF. Right? Ideally, we would say that you get this system of equations by taking a CNF and algebraizing it appropriately. However you want to do that. That'd be great. Okay, when I said, so I want to find, I haven't told you what I want exactly, but one criteria I want of f is this. Okay, So the second criteria I want of f is that it's unsatisfiable, over the Boolean cube, right? Because if it's satisfiable, you cannot find a certificate of this form. So if you prove a lower bound, that's just saying infinity is at least in your lower bound, which I can already prove. So that's not that important. Okay, so it better be unsatisfiable, and yeah, right. And then the main important thing is what Raphael is asking about, is that we want that any. This is saying this is saying there's some proof. Now we want to say that for any proof satisfying this condition, we must have large size. So for any g and h with the thing over there, the size s must be at least super polynomial, like n to the little omega 1. Okay. So that's what we really want. And so what sort of things do we know? As Tony talked this morning, and then there's several papers on this work, is that we know lower bounds depending on the definition of size. Okay, so what that means is that there are examples where we know that the degree of g and h must be, say, linear, or something like that. Okay, so that's saying that degree is some coarse measure of the complexity of a polynomial, in the sense that if the degree is very, very low, then the polynomial has low complexity. So, right? If the degree is high, it still might have low complexity in something, but ideally you can prove degree lower bounds. Right, but it's not, it's sort of a weak measure of complexity. And it's worth noting that in this case, usually you can consider f's to be multilinear, right? Because you have Boolean axioms, you're really only interested in f on the Boolean cube. So to some extent, you can assume f is multilinear, in which case there's always a linear upper bound. So saying that you have a linear lower bound is basically saying you get maximal complexity. Okay, so there are results doing this, and they basically satisfy what you want here, that f has small circuits, that they encode CNFs, things like Untitled formulas and so on. Okay, so that's one measure of complexity, but there's also other measures, and this is sparsity, right? These are a bunch of polynomials. You can express them as a sum of monomials, and you can just omit monomials that have 0 coefficients. And you ask how many non-zero coefficients do you have? That's the sparsity of the polynomial. In this case, you can also show that there are g's and h's where the sparsity is at least 2 to the omega n, or something. Right? And so this is also maximal because the g and h's are basically multilinear, and so this is saying that there are also cases where synced things that you can encode that require large proofs in these measures. Okay? But the point is that these measures are very simple, and so we have lower bounds for more complicated measures like Riemann ABPs and multilinear formulas and so on. Can we then design f's that have lower bounds for stronger notions of size? Okay, so I want to tell you about results in that way. And let me tell you now about the main f we're going to talk about. Okay, so let me remind you about the subset sum problem. Okay, so this is like a canonical NP hard problem that everyone learns in like the first theory of computation.
So, but there's no reason to expect that G and H are multilinear. Lower bounds that will be multilinear. So certainly HI won't be. Right?
Okay, so suppose that the f's are multilinear. Okay, which is more or less what we'll do. You can assume without less generally that, well, there exists a proof where the g's are multilinear. You cannot necessarily take the h's to be multilinear, and if you take the h's to be multilinear, you don't necessarily get a complete proof system.
I mean, they have to be 0. Oh, no, right.
Okay, so it's a bit subtle on how you define multilinear IPS, and I'm not going to do that. But you can you make an yes, there is a definition that makes sense, that is complete, that is sound, and so on. You don't have to look so surprised. I mean, I can talk to you about it later. Okay. So what is a subset of sum problem? It's basically, is there a subset that sums, right? So you're given beta and alpha 1 up to alpha n, and these are going to be in your field. And you want to know, is there an S, which is a subset of n, such that the summation I and s, alpha I, is equal to beta, right? right? So this is NP hard and NP complete and over the integers and so on because you encode in binary. And the thing to note though is that suppose that you had a really small field, right? If you have a really small field, then this, okay, well, let me first encode this in terms of what's going on over here. How can we take this equation, this problem, and encode it into systems of polynomial equations? And it's very easy. What you basically do is you ask, is the following linear polynomial? You take alpha I, you multiply it by xi, as I goes from 1 to n. You subtract beta I. And you want to know, is this possibly 0 when you're taking xi to be from the Boolean cube, right? And it's very clear that there is a solution to this equation if and only if there's a subset that satisfies this. Okay. Now, the problem though is that if your alpha i's lie in a small field, like F2, like say if all the alpha i's were 0 or 1 over F2, this is like a really stupid problem, right? Because there's like not that many sums you can have. So for this talk, I'm going to assume that basically the characteristic of the field, like let's just say the field is like, the rational numbers or something. Basically so that you can get enough elements so that this is actually a hard problem. Okay. Okay, cool. Right, what did I want to do? Great. Okay, so there's this paper of Impagliazzo, Pudlak, and Segal, who had the foresight to have the acronym be IPS, which is what we're talking about. And what did they show? Well, okay, so this is a subset sum thing. So in general, we don't expect you'd be able to refute this efficiently, right? Because if you could refute this efficiently, saying this is unsatisfiable, you would prove NP equals coNP. So we expect this to be hard in general. But they said, let's look at a very special case. Let's just look at the case when all the alpha i's are the same. So you have summation xi plus 1, and you have x squared minus x. So this is your polynomial system equation. It's obviously very, very simple, and obviously unsatisfiable over the hypercube. And how can you refute this? Well, what did they show? They showed that G and H you need complexity which is large here. So you need that the degree is linear. Okay? So with respect to degree, this is a maximal complexity. Okay? You also need that the sparsity is 2 to the omega n. So this is also basically maximal. So this is very, very simple, something very, very simple, but yet these two measures, very large. Okay, so it's worth noting that what I've discussed right now is all of this like static system where and Tony talked to this morning about static systems and dynamic systems. Their result is more interesting because it's actually a lower bound for the dynamic system, whereas what I'm just stating here is for static, but unfortunately there's no rug in this room, so I can't sweep that detail under the rug, but yeah, okay. Okay, so what are we doing here? Well, the question about Grotto-Potassi to some extent is, can we show size lower bounds, right? And obviously, like, showing super-polynomial lower bounds for interesting models of complexity is hard. So let's just, the goal could be, look at your favorite class of restricted algebraic circuits, try to prove circuit size lower bounds. But the question is that, it's not so obvious that even proving those lower bounds are interesting. In some sense, do you want to first prove, maybe, that restricted models of this IPS system can actually do interesting things? So I want to the first result is that. So consider this same system that I have on the previous board, the subset sum where all the alpha i's are 1. Right? We see that the degree and sparsity are large, but in fact, this has polynomial and n size refutations, the IPS refutations. Okay, so this theorem as of right now is not so interesting because you sort of expect that, right? Because IPS is a fairly general system. This is a very simple thing. But it gets more interesting because you can actually place this in very restricted classes. So there are 2 restricted classes. First, it's depth 3 multilinear formulas. Okay, so multilinear formulas is you're computing multilinear polynomials, and every gate computes a multilinear polynomial, so it's a very restricted thing. Furthermore, it's depth 3, even more restricted. And also, this is one class, and you can also place these refutations as small read-once algebraic branching programs, which are loosely related to the non-commutative formulas that Ido was just talking about. So this is saying that basically, these models of computation, we can actually prove lower bounds for them. So they are very restricted. And yet we're saying that they are exponentially more powerful in the proof setting than going on, say, with degree and sparsity. Okay, so there is something interesting to be done about proving lower bounds for IPS refutations for these models, because they can actually do interesting things. Okay, so I'm not actually going to define a lot of algebraic circuit classes here, because okay, so this lower bound is dynamic. Yes, the degree bound is dynamic.
Right, but their sparsity is really large, right? And here you're saying you have a static proof that's short.
Right.
That's also strong.
Sure.
No, you show.
I mean, yes. Yeah, I mean, I don't know. Okay, so this says that we have an upper bound, saying that we can do something much more interesting when we have these succinct measures of computation. Now I want to talk to you about a lower bound, which is the main bulk of this talk. So consider the following set of polynomials. Okay, so you have z sub I. So you're going to have two indices here: 1 less than I, strictly less than j, less than n. Okay, you're going to have a variable z sub I j. You're going to multiply by xi xj, and you're going to add 1. Okay, this is some cubic polynomial, whatever. And then you're going to have the boolean axioms, so z squared minus z and x squared minus x. Okay, so this is a system of polynomial equations. The intuition is that this sort of looks like the subset sum thing, but it's different, right? Okay, so this requires the theorem is that this requires IPS refutations of large size in two different models. So what are those? Well, let's consider read once ABP. So it'll require exponential size read once ABP IPS. So this is basically saying you write out this Nullstellensatz certificate. If you express the GJs and the HIs as read once ABPs, they require exponential size. If you say ask for multilinear formulas, there's an n to the log n lower bound for multilinear formula IPS. And there is a 2 to the n to the omega 1 lower bound for constant depth multilinear formulas. So for general multilinear formulas, there's an n to log n lower bound. For the constant depth version, you get n to the 2 to the n to the omega 1, and the omega 1 depends on the constant depth. It's like 1 over the depth-ish.
But the same lower bound is Razi.
Raji Yehudev, yeah.
Razi,
Yeah. So in some sense, what's going on here is that we're not actually proving new lower bound techniques in a circuit sense. What we're doing is we're looking at what the circuit lower bound techniques that are out there, and we're sort of adapting them to this situation. Okay, so basically these bounds are the same thing that we know for computation, suitably imported. And there's, yeah. Okay, so are there any questions about the theorem statements? Because now I'm going to sort of talk about, Newton. Yeah. Okay, so it says you have this weird looking cubic formula with the Boolean axioms. Take any expression of this form. The at least one of the GJs or HIs must have complexity of this form. N2 and 3. Yeah, simultaneously. Yeah, so there's this imaginary rug in the room. That's where it is. Yeah. So yeah, there's some definitional quirks in what multilinear formulas are based on Raphael's question, because this is not a multilinear polynomial, and so you multiply. What? Yeah, so that's also on the rug. Okay, so to some extent, what Odo was asking about, and this is what Pavel mentioned, is that in this expression, okay, this is linear in the f's and it's linear in the Boolean axioms. Okay, so this is a general Nullstellensatz certificate, but Grochow and Patasi defined a more general notion where you can have dependencies on the f's and the Boolean axioms which are nonlinear. And the reason this is sort of interesting is because, you know, maybe you could combine them in interesting ways and work in the ideal where you have things like f squared and f cubed, and maybe that would help you somehow, where you, because like actually like multiplying your axioms together. And one of the things that we actually show is that in general, IPS is equal to this IPS lin. Is that how we tried to? I think that was the notation we settled on. Okay, so if your axioms are of small circuit complexity, which they sort of should always be, then this general IPS system that Grochow and Patasi defined, you can always simulate it with the linear version. This won't necessarily be true in restricted models like the ones I stated over here, but that's where we can prove lower bounds, so that's why I'm trying to, there's a rug. The linear version is what I defined here. This more general version is where you have a circuit, C, and you have X, and you have Y, and you're going to like plug in your axioms here, and you're working like these X's encode your G's, and the Y's encode how you deal with the axioms. And you have certain stipulations on how this works. Okay? Yes, in general you're allowed to multiply your axioms together and do non-trivial things there. Yeah.
Before you do anything about the curve, you could give us some idea of how to get the upper bound in the top case, and then why when you have the product of the two of them.
Like this lemma, you're saying? Or
The first theorem of
this one.
with an upper bound. Could you give us an idea
Yeah.
why that works, and then maybe we'll see why, intuitively, why it shouldn't work for the second one.
Why it shouldn't work for here. Yeah, okay. Okay, so the intuition for the upper bound is as follows. Suppose you have summation xi, right? How many values could it possibly take? Right, there's only n plus 1 values, right? So over the hypercube, this is definitely in 0 up to n. Okay, so let's define p, which is a univariate polynomial, which is just the product. I goes from 0 to n, and this is t minus I. Right, so this is saying that p of t, p of summation xi, is congruent to 0 modulo the hypercube. Right? And so, to some extent, what we want to do is we want to prove, like, yeah, okay, so this is fine. And then what do we do? Right, so then we consider the following, that we, yeah, so then, but the point is, yeah, p of minus 1 is not 0, right? And then we observe that you can consider the following. So consider p of the summation of x minus p of minus 1. This is divisible by summation of xi minus minus 1. This is not, you can see that this is in fact a polynomial. It's not super hard. And if you multiply this by summation xi plus, so this is summation xi plus 1, and you multiply by like this is congruent to 0 modulo the hypercube, right? And so, oh no, sorry, this is congruent to, yeah, minus p of minus 1, right? And this is a scalar, right? So I want to call this to be my f of x, or g of x. Right, so this is saying that if I just worked modulo the Boolean hypercube, I have a g of x times my axiom equals a scalar. So that's already a witness of unsatisfiability, right? And so what you need to show now is that, so now you need that, number one, g of x is efficiently computable. And then two, that you need to show that the hi's are efficient. Right? And so the g, you know, based on what Pavel already mentioned, I mean, this clearly has a small algebraic circuit because it's just a small algebraic circuit. And then you can divide because of Strassen elimination of divisions or doing other things. So that basically already says that G has a small algebraic circuit. That's sort of clear at that point. To put it actually in these classes, you know, you sort of stare at it until your eyes bleed. Okay, but number two, I mean, you need to show that you can sort of efficiently multilinearize to some extent, right? That you have something which is 0 modulo the hypercube, and you need to somehow actually do that successfully. And the point is that in general, multilinearization is not an efficient process, but because you can put these, like, it's not just efficient as a general circuit, but it's efficient in these models, you can efficiently multilinearize. Intuitively, like, if you have a multilinear formula, it's pretty easy to multilinearize multilinear formulas on some level, right? So that makes it pretty clear that you can do this on some level. Okay, so that's the rough intuition why the upper bound works. And then you had a second question, or why it doesn't work for these, or something. Is that okay? Great. Okay, so those are the results. Now I want to tell you about two ideas on how we get lower bounds. Okay. Okay, so let's look at our Nullstellensatz certificate, right? We have g of x times, suppose that, okay, so let me comment briefly on why our results are not so amazing. In the sense that here we have our Boolean axioms, and we have one non-Boolean axiom. And the fact that we have sort of one non-Boolean axiom seems an inherent limitation of our approach, and I'll sort of try to explain why. And furthermore, we're not getting encodings of CNFs, because encodings of CNFs would be many axioms. You do it clause by clause. Okay? So in some sense, there's still work to be done, and this is to some extent a first step. Okay, so let me explain though, in the case that you have one non-Boolean axiom, how you can expect to get lower bounds. So in this one non-Boolean axiom case, you have something like this, right? You have this Nullstellensatz certificate, and you want to conclude that either G is large or some of the HIs are large. Now, the first idea is what I'm going to call a lower bounds for multiples. It turns out that this approach has certain deficiencies with respect to getting proof complexity lower bounds, although there's some hope on how to extend that. But it's independently interesting, so I just sort of want to tell it to you. Yeah. Okay, so the idea is that you take this expression, and you just move the second part to the other side. Okay, so what do you get? You get g times f is equal to 1 minus summation hi xi squared minus xi, right? The first thing to note is that this is a non-zero polynomial, because if you just plug in a Boolean value, you get 1, because this entire thing vanishes. Okay, so this is non-zero. Okay, now what this is saying is that, say now that this is a size S circuit. Okay, that implies that there's some multiple of f with a size S circuit. Right? G times f has a size S circuit. F is what you get to pick. Right? So if you can just rule out that f has every multiple of f requires large circuits, then this simply cannot happen. Okay?
Wasn't one of the requirements that
Yes. So you caught me. Okay. So what Ramprasad is saying is that actually requires that f itself is hard, which means that this does not satisfy this idea. Okay. But there's the following. This is not working, but there's the following hope, which is that f itself might be hard, but you could hope to use extension variables to convert to something easy. So what I mean by that, instead of you take f, which requires every multiple to be large, and then you encode as sort of, f1 up to fk, or fs or something, I don't know. And roughly speaking, what this should sort of do is, this will only work sort of for restricted classes to some extent, but what you hope is that these FIs should be encoding the local computation graph of f itself. Okay, so for example, let's consider the following.
Maybe you want to say f can be commutable by some general set.
Right. Right, so let's just take a very simple example. Suppose that you have f is the product of xi plus 1 or something. I don't know. I don't know, make it pick one accordingly. Okay, so this is a complicated polynomial with respect to like depth repowering or something like this, right? But you could do something like you take x equals y times z, y is equal to a times b, z equals c times d, and I'm running out of letters. But like by tracing through this graph, you can compute large monomials. So the point is that this polynomial is hard with respect to very restricted classes, but you could, because it has a small circuit itself, you can replace it possibly with local axioms, and then you get a system where everything is simple. The problem is that right now we don't know how to prove that lower bounds for multiples can be extended to this system here. So this is sort of to some extent a full, first step, and an idea on how you could possibly hope to lift lower bounds for circuits to lower bounds for proofs. Okay, to some extent the real reason I'm telling you about it though is because lower bounds for multiples has very natural connections with things like hardness versus randomness and polynomial identity testing and so on. But because it doesn't actually give you legitimate proof complexity lower bounds, I'm not going to tell you too much more about it. Okay. So what I want to tell you now is a different approach, which is so-called functional lower bounds, which Ramprasad will talk more about on Thursday. Yeah. Okay. So again, we have our single non-Boolean axiom, and we have our Boolean axioms. And again, the Boolean axioms are really annoying, so I want to work modulo the hypercube. So if you look at this equation and you just work modulo the Boolean hypercube, you get that g times f is congruent to 1 modulo the hypercube. All right, so this is an ideal, but you can also instantiate this equation for every x on the hypercube functionally. Right? So you get g times f is equal to 1 for all x in 0, 1 to the n. Okay. Now the point is that we're really using here that f is unsatisfiable because, if f was ever 0, then 0 times something non-zero would be 0. So certainly, f and g are both non-zero for every value in the hypercube. And because they're non-zero, we can divide. Right? So this says that g of x is equal to 1 over f of x for all x in the hypercube. Okay, so this all seems very stupid, but I want to dwell on this for a moment. And why is that? Well, g is a polynomial. Okay, this thing here, no longer a polynomial, but I can think of this as a function. Let's think of this as a function f hat, which maps my hypercube to the field itself. Okay, so f is a function, and I'm saying that g agrees with f hat on the hypercube. And so what is a functional lower bound? A functional lower bound is some function on the hypercube such that whenever you have a polynomial g agreeing with that function, it must be large. Right? So if g on the hypercube is equal to f on the hypercube, we want to say that implies that g of x is hard. Okay, and you can expect such things to hold in the sense that look at the permanent, right? The permanent on 0, 1 matrices is sharply hard, right? So if there was a small algebraic circuit that agreed with the permanent on 0, 1 matrices, that would collapse the hierarchy, right? So it shouldn't be, if you just look at the, if you just take the permanent here, you should hope this to be true if the polynomial hierarchy doesn't collapse. And so you could hope to prove this for like restricted notions of circuit classes and do it unconditionally. Okay, and so that's what we're going to do. Okay, but the point is that both of these methods are really looking at the fact that you have one non-Boolean axiom. If you had two, it's not really clear how you deal with this. And in particular, this one doesn't even deal with the non-linear IPS. This only works in the linear case. Okay, so now I'm going to go into the details. Are any questions on these two sort of ideas? Okay, lower bounds is actually, here you can actually do more. You can do more axioms, but the functional one is really just for one. Certainly, if you had like for the nonlinear case, if you had an f and you had an f squared, like if you had a nonlinear dependence on f, it's not really clear how you could separate the g's and f to this sort of side. Right? Okay. All right, so now we want to do some details. So the first thing I want to do is just review this IPS 99 statement that you have it is right here. Cool. Okay, so the degree is at least linear, right? Okay, so I'm going to phrase this now as a functional lower bound. I guess I could actually do it over here. Okay, so the lemma is that suppose that you have a g of x, and you multiply it by not this hard thing I'm actually going to do, but the subset sum axiom here. Suppose you multiply this by summation xi plus 1, and suppose that this agrees with 1 on the hypercube. what I want my conclusion to be is that G should have high degree. Now, the statement over here is that it's linear degree. I actually want to get that the degree must be at least n. Okay, and you can see that there exists a G where the degree is actually n. So this is a really sharp bound, and the fact that we're getting the sharp bound is important for us. Yeah. Okay, so how do we do this? Right, and this will also imply that the sparsity in this proof will also get not just 2 to the omega n, we'll actually get sparsity 2 to the n. So it'll actually be the actual maximal sparsity possible. Okay, so what do? We basically follow the functional lower bound idea. We get that g of x is equal to 1 over summation xi plus 1, right, for every x in the hypercube. Okay, so g is a polynomial, and it has this a functional equation. Right, and basically what we do is we just look at the fact that every function has a unique multilinear polynomial agreeing with it. Right, so we can consider this multilinearization operator, which takes f of x to f of x, and basically replaces a polynomial with its multilinear version. Right, and the point is that the degree and the sparsity basically only go down. Okay, so if we can prove lower bounds for the degree and sparsity of the multilinear version of G, then we're done. Okay, and basically the point is that the multilinear version of G is uniquely determined. Right, because as Pavel was saying, is that if you look at the hypercube, there's a unique multilinear polynomial agreeing with this functional equation. So basically what you do, there are at least 2 different proofs in the paper, but what you basically do is you compute this multilinear polynomial. It is unique, and you just say, aha, the degree is what it's supposed to be, and sparsity is what it's supposed to be. And then you're done. Okay, so that's pretty simple. And it gives you this lower bound for the generic one. But now we want to basically lift this to a circuit lower bound for this stuff. Okay. So what I need to do though is I need to tell you how do you prove circuit lower bounds of this kind. Okay, so I need to tell you about a complexity measure, which is the so-called evaluation dimension measure. Okay, so suppose that you have an f of x, and I'm going to break it into 2 parts. So there's going to be a partition of the variables x and y. And is that what? Yes. Right, and I'm going to choose some subset of my field. What I basically want to do is I want to take y and just evaluate it every possible way using values of s. Okay, so I'm going to define the set of partial evaluations in the xy partition in the set S of f to be this set. You take f, x will be unchanged, and you take alpha, where alpha basically comes from, you take y and you just replace every possible value of s. Okay, so this is some infinite set, or possibly infinite set of polynomials. But the point is that this lies in the space of all polynomials, which is a vector space. And then our complexity measure will just be the dimension of the valuations of f. Okay? And so this is not necessarily what we talked about in the boot camp, but you can show basically that there's a fact that this is equal to the dimension, the rank of the partial derivative matrix. It's equal to the rank of the partial derivative matrix. Or rather, it lower bounds the rank of the partial derivative matrix. Sorry? Okay, so here's the mu will depend on s, and for all s, this is a lower bound. Okay, so if you take s large enough, it'll be equal, but for any particular s, it'll be a lower bound. Okay. And so the rank of the partial derivative matrix is a well-known technique for getting circuit lower bounds. In particular, circuit lower bounds for Riemann ABPs, multilinear formulas, particularly of constant depth, and so on. So basically, if we can show that this evaluation dimension is large, then we can get the circuit lower bounds that I promised. Okay. And the key point about this evaluation dimension is that it is functional in a certain sense, right? Because all we're doing is we're taking this polynomial and we're evaluating it at certain points. right? And the point of a functional lower bound is we're only told that we have a polynomial and it agrees with some function, right? So we can't actually do things like take partial derivatives. If you take a partial derivative of a polynomial, like you can't actually learn anything about a partial derivative. Like if you have a univariate of degree d, and you're only told the value of this polynomial on 2 points, you can learn nothing about its first partial derivative. Okay, so you really have to use a functional measure, and that's why we're using a functional measure. We can't use we can't use the partial derivative matrix itself because G could be of large degree. That's why we're using evaluations instead, in which case we only get a lower bound on the rank of the partial derivative matrix. Okay. Right. Cool. Okay, so the theorem here is basically we just want to say that if you have a g of xy, okay, so over there I said that there's a lower bound for all those models. I'm going to do a simpler version right now, which is suppose you just consider the inner product function. Okay, so you're going to have n variables, each n x's and n y's. This is summation 1 to n. You take this inner product and you add 1. It's clearly going to be unsatisfiable over the Boolean cube. Okay, and so suppose now you have that g times this inner product plus 1 is equal to 1 modulo your Boolean axioms, x squared minus x and y squared minus y. We want to then say that this implies that our measure, like this evaluation dimension over the set 0, 1 of g is at least 2 to the n. Okay, and this is also maximal. Okay, just as we had degree maximal and sparsity maximal, we're going to get a maximal bound here because there is a g that meets this bound. Okay, so it's like super tight. Okay, so what is the proof of this? Okay, so again, we're just going to use this functional perspective to say that g of x y is equal to 1 over the summation xi yi plus 1, right, for everything in the hypercube. And now we want to understand what are the evaluations, or like the partial evaluations look like. Well, we have this xy partition, and we're going to evaluate y over the set 0, 1. And what happens when you do that? Well, basically what's going to happen is you're going to zero out some of the x's and keep some of the others, right? So what you're going to get is you're going to get a set of polynomials, g of t. They're only going to be in terms of x's because we substituted the y's. And we're going to think of t as coming as a subset, right? Because if you're evaluating y over the hypercube, you can identify the hypercube with subsets. And so we get this. And what do we know about g of t? Well, functionally, g of t is basically this thing, the function, what you would expect, summation xi plus 1, where now I only comes from t, right? So yi will pick out, you set yi accordingly, it'll pick out the t's that you sum over, and that's the functional equation for g of t. Okay, so the point here, though, is that this set is a set of polynomials. Okay, because I partially evaluated y, you have a set of polynomials. But the claim is that the dimension, the mu over 0, 1 is at least, so this is the dimension of a set of polynomials. You can lower bound this as a dimension of functions, right? So this is lower bounded by the functional things here, right? So now you look at the set of functions xi plus 1 I and t for all t and n. Okay, because possibly these g of t are of high degree, right? And we're just looking at basically their action on the hypercube. That is a set of vectors. Each of these is a function on the hypercube, so it's a vector of 2 to the n size. We want to say that this dimension is lower bounded, and this is sort of clear because evaluation is a linear operation. Okay, and now the second claim, we just need to lower bound this guy, is that this dimension is equal to 2 to the n. Right? Basically that this is a set of functions, and I want to say that they're linearly independent. Okay, so I could just give, kind of late in the day, I could just give this as an exercise, but let me prove it for you. Let's look at the multilinear representation of 1 over summation xi plus 1 I and t, right? So I'm going back to polynomials, basically. That, this is a function. You look at its unique multilinear representation. What does it look like? Well, how many variables does this depend on, right? It only really depends on the variables in t itself. So the degree is clearly at most t, okay? At least on an intuitive level and on a formal level also, okay? But what did we prove over there? right? We proved basically that if you look at the subset sum axiom, functionally, you must have a degree lower bound, right? So what our degree lower bound from there says the degree is also at least t, right? But the point is that this is a multilinear polynomial. How can it have a degree, I mean, this is saying the degree equals t, right? How can it have a degree equal t polynomial? That means that the monomial, the product of int xi appears, right? Because this is the unique, degree t thing that can appear here. But furthermore, because this only depends on the variables in xi, this is the leading monomial. This is like the biggest monomial that can possibly occur. Okay? And note that this leading monomial is uniquely determined by your set t, so that implies that all the leading monomials are distinct in this entire set, right? And basically that means that you have a triangular system of vectors, which implies that they're all linearly independent. Okay? So you have these polynomials, which you got from partial evaluations of your functional equation. You look at their multilinear representations, you look at them as polynomials, and you basically get that they're a triangular system, and that implies they're linearly independent, which says that the evaluation dimension is at least 2 to the n as we wanted. And then basically you just go to these other papers and say, what kind of lower bounds can you get from evaluation dimension? And that's how you get your circuit lower bounds. Now, it's worth mentioning that in this evaluation dimension thing, there's a partition between x and y. Okay? And there's some idea that maybe you could look for every partition instead of just a fixed partition. And that's why we defined this cubic polynomial as we did. Right? The idea is that this cubic polynomial, you can kind of think of it as a complete graph. Basically, you have, this is terrible board work, I'm sorry. But if you have a bunch of vertices here, right, where each vertex is sort of like, well, you have a bunch of vertices. And basically what you can do is you can set the z's such that no matter how you partition this graph, you can find a bunch of edges that cross here. And then you just embed this inner product into this thing. Okay, so this way you can go from a fixed partition to any partition. And basically what you can get is you can get something that in every partition the evaluation dimension is full, which readily gives these lower bounds. Okay, so I think that's all I wanted to say, so thank you. At least I don't think, but it'll work for depth because essentially you just need to do homogenization. I mean, okay, if the axioms are low depth and C is low depth, then it's fine. Yeah. Okay.